Okay, in this video we're going to talk about Jensen's inequality. And I'm assuming for this video that you're familiar with measure theory, basic measure theory, and so that I can state this theorem, this inequality, using measure theory. Because it's really a measure theory result. But here's how it's presented in an undergraduate probability course. So suppose that you have a function that's convex. So let's say that phi is a convex function. Convex functions are often called concave up. And what it means is that the second derivative is always non-negative. So the derivative is always increasing. And some examples of this are phi of x equals x squared, and phi of x equals 1 over x as long as x is positive. And phi of x equals x is also concave up because the second derivative is 0. But that's okay because we just require that the second derivative be greater than or equal to 0. So concave up functions. And suppose that you have a random variable x. So phi is a convex function. X is a random variable. Okay, capital X. Then the theorem, which is Jensen's inequality, is that if you take the expectation of x, that's a number, and you plug that into phi, your convex function, that is going to be less than or equal to what you get if you take the expected value of phi of x. Okay. So just to clarify what's going on, so the left-hand side is a number, right? You take the expected value of x, that's a number, you plug in phi, you plug that into phi, that is going to give you a number, so you have a number on the left, and on the right, you take your random variable x, okay, you take phi of x, so phi of x, remember what that means is x being a random variable, x is a function. So phi of x really means phi composed with x. So you do x first and you do phi. So that's a function, and you take, this is a random variable, and then you take the expectation of that. So the Jensen's inequality is saying that the left-hand side is less than or equal to the right-hand side. Okay. And in this video, we're going to prove the facts. So this is Jensen's inequality. Or maybe it's pronounced Jensen. I think it's a, I don't really know how to say it. But we're just going to go with Jensen. And I'm going to give a proof of this using measure theory, because this is really a measure theory result. And so I'm going to restate the theorem and prove it in that context. The context is, suppose that you have a measure space and you have a probability measure, say P, or well, let's just call mu. So mu is the probability measure. And recall what that means is you have some measure space and your measure just has value 1 on the entire space. Okay, we're going to use that fact. And suppose that f and phi of f, so again, phi is a convex function. Suppose that f and phi of f are measurable, are integrable. Okay, so phi of f, just to remind you, means phi, this means phi composed with f. Then Jensen's inequality says that if you take the integral of f over your measure space, and then that's going to be a number, you plug in phi, that is less than or equal to the integral of phi of f, right, with respect to the measure. Okay. And here's a proof of this. So the way to prove this is, so you have this convex function, and there are several ways of thinking about a convex function. So one way I think about a convex function is that whenever you have a point on the graph and you look at the tangent line is always going to be below the graph of the convex function. So this is hopefully a familiar fact from calculus, that if you have a concave up function, the tangent line is always an under approximation. It always lies below the graph of the function, except for where they intersect, of course. And intuitively, right, what's going on is they have the same derivative at the intersection point, but since your function is concave up, the slope is increasing, and so it's going to move away from the line, and it'll be above the line because the slope is increasing. Right? And similarly, to the left of the intersection point, if you think about it, if to the left of the intersection point, the slope of the graph is going to be less than the slope of the tangent line, but in order for them to intersect, it had to have been the case that the graph of the function is above the tangent line. If you just think about it intuitively, that's what's going on. Okay, that's not a proof, but it's the intuition behind why it's plausible that this is true. So you take the linearization at this point. Now we're going to take the linearization at the value of the integral. So let C be the integral of f over your space. Okay, so we're going to look at the linearization at C. So let, say, L be the linearization of phi at C. In other words, it's the linear function whose graph is the tangent line at C. So L has the form L of x equals ax plus b, right? It's a linear function. And A is going to be phi prime of C. We don't need that fact, but just to be clear, A is going to be the slope of the tangent line, phi prime of C. But L has this form with L of C equal to phi of C, and phi of x is greater than or equal to L of x for all x. That's just stating the fact that the graph of the curve is higher than or equal to the graph of the line. Okay, and this is where we use the convexity, right? This inequality. This is where convexity is used. And it's just a simple estimate, so we have that the integral of phi of f must be greater than or equal to the integral of L of f, because phi is greater than or equal to L. And what's L of f? That's just AF plus B, right? And now by the linearity of the integral, this is equal to A times the integral of f plus the integral of b. And now here we use the fact that you have a measure space, because I have A times the integral of f, but what's the integral of b? So b is a constant. What's the integral of b? I have a probability measure. So the integral is going to be b, right? It's just going to be b times 1, which is b. So to go from here to here, this is where we use the fact that mu is a probability measure. Okay, so it's just A times the integral of f plus b. Now what is that? That's just what you get. So this integral, right, this is what we define to be c. So this is just A times c plus b. Well, A times c plus b is just what you get when you plug in c into L. So this is L of c. And L of C is equal to phi of C. And phi of C, right, this was by definition that they're equal. And phi of C is by definition phi of the integral of f. And so when you put it all together, you see that this quantity is greater than or equal to this quantity. Let's use a lighter color. Right. This greater than or equal to that, which is exactly what Jensen's inequality says. So that's the proof of Jensen's inequality. So really a very simple proof. And what you do is you just take the linearization at this number. Okay, you take the linearization, and then you just, because you have this inequality here, you just apply it to the integral, and you have a probability measure, so this integral ends up being just b, and then you get the result. And so how does this reduce, well, not reduce, but how does this relate to the other version of Jensen's inequality, this version? Well, recall that the expectation of a random variable is the integral of x with respect to the probability measure, right? So by Jensen's inequality, you get that phi times the integral of x is your function f. So this is less than or equal to the integral of phi of x. And so the left-hand side is equal to phi of the expectation of x. And the right-hand side is just the expectation of phi of x. So that's how you get the result. So one kind of neat application of this, I mean, this is kind of like a trivial application, but if you take phi to be x squared, so phi of x to be x squared, then what does the inequality say? It says that if you take the expectation of x and then you square it, that's less than or equal to the expectation of x squared. And we know that to be true from our discussion of variance, right? Because recall that the variance of x can be defined to be the expectation of x squared minus the square of the expectation. And so therefore, this is greater than or equal to 0. Maybe I should just make it clear that this is a little x here, and then this is a capital X. Okay. I mean, you don't need Jensen's inequality to prove this inequality that the variance is non-negative, but it's just a little application of it. Okay, thanks.